All right, everybody. Very good to see everybody here again. Hope everybody had a good weekend, ready for the lecture today. I don't know about you guys. Doesn't it feel like, I don't know, like half an hour we were just in here last week and now we're back here already? Is that just me, or I don't know where this whole last week went, but there we go. Okay, so today we're going to keep on thinking about electronic circuits and the physics of them, and we're going to be focusing on two absolutely key, absolutely essential kinds of electric components. So as you can read there, we're going to be thinking about resistors. Now I brought along some resistors here. We've got a little resistor over here. I guess you guys probably can't see that if you're at the back. It's a pretty tiny one. Got a slightly bigger resistor over here. Can you guys see that, the little resistor over there? So that's a very, very key kind of electronic component. We're actually going to be using these in the labs in a few weeks. So today we're going to be finding out, what are resistors, why we use them, and the physics of resistors. And then also we're going to be thinking about capacitors. Now the capacitors I brought along with me, they're a bit bigger. So we've got a slightly bigger capacitor over here. Now, there's some very important differences between resistors and capacitors. We're going to be learning what they are, learning about the physics of capacitors, and with both of these, so the resistors and the capacitors, we're going to be learning about how to combine them in circuits, so how to build circuits and the kind of things we can get with that. But the thing I want to prioritize with both of these is that when it comes to these components, how many of you have studied them before, resistors and capacitors? Okay, so some of you have done them before. Okay, so if you have done them before, like some of the things we were studying last week, there are quite a few fairly simple equations that you can memorize and you can use, and you can calculate things related to these components. But like I emphasized last time, that we are studying further physics here, not just electronics. So what I'd like to do with these components is approach them very much from a physics point of view. So thinking about applying the physics concepts that we've been learning and seeing how they apply to these kinds of components. So we're thinking about charge, so how we can store charge, how charge flows, and also thinking about energy. That's a very important part of this. So even if you have studied them before, maybe the approach we're going to take when we're thinking about the components here, it might be a bit different to how you've seen them before. So let's start by thinking about resistors here. So I got a little resistor here, not much bigger than a grain of sand. They put the little stripes on, the colored stripes, so that you can see, what kind of resistor it is. So let's start by thinking, well, what really exactly is a resistor from a physics point of view? Obviously it's a component. You can put it in your circuit. You can get it to affect the current in your circuit. But what really is a resistor from a physics point of view? So I've got this question over here. We can start thinking about this from a physics point of view. So in a resistor, I think if we're defining what it is, it's really anything where the voltage across the component is directly proportional to the current. So if we double the voltage, maybe if we put twice as many batteries in, then we're going to get twice as much current, okay? That's really, from a physics point of view, a pretty good working definition of what a resistor is. So maybe you've seen this equation to define this before, but if not, you can figure it out. Okay, so which of these equations describes this relationship mathematically? Let's see what everybody thinks for this one. So if you've studied resistors before, maybe you can remember this equation, very famous equation, whenever we're thinking about resistors and electronics. If you haven't seen it before, that's absolutely fine. You don't need to guess. Which of these equations here do we have that the voltage is directly proportional to the current? That's all we're looking for in this equation. All right, let's see what everybody thinks for this one. Which one of these equations describes this relationship mathematically? Okay, so some people going for all of them, but it looks like most people are going for option B there. Now you don't need to guess with these ones, okay? Because we've got this, in a sense, isn't it a sort of empirical result that we have these things, and if we double the voltage, if we triple the voltage, then the current doubles, current triples, okay? So the only equation here which describes this as a kind of directly proportional relationship, it's this equation here, so equation B. So very well done, everybody who gave that question a go, especially if you got that it's option B. Okay, now who's seen this equation before? Okay, so a fair few of you. So does anybody know what this equation is called? Oh yeah.
Ohm's law.
Ohm's law, fantastic, 100%, okay. So it's called Ohm's law, okay. And it's really just a mathematical description of this experimental relationship, the relationship between current and voltage. And we've got this proportionality relationship, and as we say, the constant of proportionality, so the thing which relates the current to the voltage, that's what we define as the resistance. So, you know, we've got some different kind of resistors here, some have a higher resistance than others, and it's really what that constant of proportionality is which defines what a resistor is. So that's Ohm's law. We're going to see it over and over again. You're really going to get very familiar with that equation, okay? So that's the basic relationship between current and voltage in a resistor. But let's think about that constant of proportionality, okay? So we got our resistor here, and the resistance, it's measured in units that we call ohms, okay? So after Ohm's law, okay? So that's the Greek symbol omega. So the units of resistance are ohms, okay? But let's think about how can we relate 1 ohm of resistance to volts and amps. Let's have a think about this one over here. So again, with this one, you don't need to guess if you haven't seen resistors or Ohm's law before, because we know that voltage is going to be measured in volts, and we know that current, it's going to be measured in amps. So we know what's going in and we know what's coming out. So with just a bit of algebra, we can work out what the units of our resistor, that R, has to be in order to give us something with a voltage units of volts. So you don't need to guess, you can work it all out with just a bit of algebra. All right, let's see what everybody thinks for this one. What's 1 ohm in terms of volts and amps? Let's see what everybody gets. Okay, so again, well, nobody's going for A and D. Some people may be thinking it's C, but when you do the algebra, when you work it out, we get option B over here. So 1 ohm of resistance is equal to 1 volt per amp, okay? So those are the units that we use to measure how sort of strong, how big a resistor is, how much resistance it's going to provide to our circuit. So this resistor over here, so 7.5 kilo ohms, so pretty substantial resistor actually. If you put that in a circuit, that's going to provide a fair bit of resistance to your current. And this resistor over here, you know, even though, you know, it's pretty small, so that's a 15 kilo ohm resistor, okay? So pretty significant resistance there. And when we do the lab in a few weeks, you're going to try what happens when we sort of use various different resistors, see what happens with that, okay? Now, very often when we're building circuits, I guess it's almost a bit like Lego. How many of you guys like had Lego or still do, right? Not say who's got some experience with Lego, right? Okay, so quite often you're making something out of Lego, and you know you don't have exactly the right part for what you need, right? So you have to be a bit creative. You know, you have to put the different parts together based on what you've got, okay? And sometimes when you're making circuits, we get in a similar situation. So maybe, you know, you've got these two resistors over here, but this resistance isn't exactly what you want for your circuit. So very often when we're using resistors, we use them in combination. So we have multiple resistors combined in a circuit. So it's very important to think about the physics of what happens when we combine resistors together, okay? So let's think about a couple of different ways that we can combine resistors here. Okay, so I've got an example of a circuit here. So we've got maybe two resistors, they're connected to a battery, and we're measuring the voltage across both of them here. So a pretty simple circuit where we've got two resistors. And what we're thinking about in this question is, if we have these two resistors in series, what's going to be the effective total resistance from having these two resistors combined together like this? So we can start to think about the physics of this, okay? So a couple of points to think about, okay? So remember from last week when we were thinking about circuits, thinking about components in series. So whenever we have components in series, the current is the same. So whatever the current going through resistor A is, that's going to be the same as the current going through resistor B. So that's our first kind of hint that we need to figure this one out. Now for any resistor, we know that voltage is equal to current times resistance, okay, so from Ohm's law. And that's true when we're thinking about resistors individually, or if we're thinking about this kind of hypothetical resistor made from combining the two resistors together. And then the last piece of the puzzle that we need to figure this one out. So from last time, so on Friday, we think about voltage. So in series, the total voltage adds together. So, you know, maybe that's a 9-volt battery over there. You know, if we've got 5 volts going over there, then it's going to be 4 volts going over there. Okay, so in series, the total voltage adds together. So those are all the pieces of the puzzle we need to figure this one out. Okay, so if we have our 2 resistors, which of these 4 options is going to be the equation for the combined resistance that we get when we put these 2 together? So again with this question, if you have studied resistors before, maybe you've already seen this equation for how to combine them. If this is the first time you're doing resistors, you haven't seen this before, you can figure it all out. Okay? You don't need to memorize anything. We know that the voltage adds together, we know that the current's the same, and we know what Ohm's law is. So we have all the pieces of the puzzle there. So let's see what we get when we put them all together. What do we get for the total resistance of two resistors when we combine them in series? All right, very good to see those responses coming in. Let's see what everybody thinks for this one. Let's see what the responses are. Okay, so some people going for all of them. Okay, now that's all right, because I like to see that you guys are thinking about this, that you guys are figuring it out for yourself. Okay, so let's see what we've got here. Some people going for D, B. It looks like most people are going for A. And really the key to this is this idea that whenever we have components in series, the total voltage adds together. So our total voltage is just equal to the voltage going across A and the voltage going across B. And this is the key we need to unlock the puzzle, because what we can do is for each of these voltages, we can substitute in this relationship over here from Ohm's law. Okay, so V equals IR for the total and for A and B. Okay, and then the last piece of the puzzle that we need is that in a series, the current is the same. So those currents are just going to divide out, and what are we left with? We're left with this one over here. Okay, so our total resistance is equal to resistance A plus resistance B. Okay, so very well done everybody who gave this question a go. Correct answer is option A. Okay, so very well done everybody with that one, because that's a bit of a tricky one. Have to figure things out a bit more. Okay, so well done everyone with that question. Okay, now that's a very important relationship whenever we are combining resistors. Okay, so I think maybe let's try a kind of numerical example, see a bit more how this works in practice. Okay, so maybe we're making a circuit. We've got a 9-volt battery. You guys know the 9-volt, the kind of the squarey kind of rectangular batteries. Okay, we've got a 9-volt battery, and we got resistor A is 11 ohms. Okay, so maybe that's just what we've got in our electronics drawer, and we want to have a current of 500 milliamps. So that's what we're going for. Maybe, you know, we're making a USB charger. Remember from the first lecture, that's the current that we want. So the question here is, what should resistor be? Which resistor should we pick out from our drawer so that that's going to give us a current of 500 milliamps? So there's a couple of steps to this one. Let's see what everybody gets for what that resistor B should be to give us that correct current. So this is a bit of a tricky question because there's a couple of steps to it. So if you're not sure, a good place to start with this one is by thinking about what our total resistance needs to be. So we know that we have a 9-volt battery, and we know that we want a current of 500 milliamps. So from that, we can work out what our total resistance has to be. And then we know that one of our resistors is an 11 ohm resistor, so then it's quite easy to figure out what the other resistor should be. So there's a couple of steps to that one. So take your time with the math, take it step by step, and then we'll see what everybody thinks for this one. All right, let's see what everybody thinks for this question. What have we got over here? Okay, so nobody's going for D. Looks like most people are going for B. So if you just take this question from the top down, so we got our 9-volt battery and we want half an amp of current. So from Ohm's law, V equals IR, that tells us that we need a total resistance of 18 ohms. Okay, so our total resistance, our RT over here, that's got to be 18 ohms. And then our first resistor is 11 ohms. So then, you know, the last part's pretty easy. We can figure out the difference. It's got to be 7 ohms over there. So correct answer is option B. So very well done, everybody who gave that question a go, especially if you got that it's option B, because, you know, it starts to be a bit tricky when there's a couple of steps to it. Okay, so very well done, everybody, with that question over there. So that's combining resistors in series. So, you know, if you've got the 15 kilo ohm resistor and we got the 7.5 kilo ohm resistor, if we combine them in series, that's going to give us, you know, 22.5 kilo ohms of resistance. Now that's combining in series, but remember that we can also combine things instead of in series in parallel. Okay, and that makes things a bit more interesting. So let's take a look at what the circuit looks like when we've got things in parallel. So remember, in parallel, that just means that that's how they're connected in our circuits here. So let's think about with this question, if we have two resistors connected in parallel, what's going to be the total resistance? What's going to be the expression for the resistance? Okay. Now the key to this question is that whenever we have any components in parallel, the voltage is the same. So if we went to measure the voltage across A or B, we're going to get the same voltage. Because they're connected in parallel, the voltage has to be the same. Then the other thing that we're going to need to know for this question from last week is that whenever we have components in parallel, the total current is the sum of the current. So if we have a certain amount of current going through A, a certain amount of current going through B, the total current, we can just add that together. So we have the current and we have the voltage figured out. And then for any individual resistor, we know that the current, it's just the voltage divided by the resistance. So we have all the pieces of the puzzle that we need to figure this question out. We just need to put them all together to see what our total resistance is going to be. So I'll get the question going, have a think about this one, and in a moment we'll see what's the total resistance when we have two resistors combined in parallel. So again with this question, if you've done resistors before, maybe you've already seen this equation. If you haven't seen this equation, no problem at all, because we've got everything we need to figure this question out from these pieces of the puzzle. We just got to put it together, and that's going to tell us what the total resistance is when we're combining resistors in parallel like this. Okay, very good to see those responses coming in. Let's see what everybody thinks for this one. What do we have here? Okay, so nobody's going for B this time. Most people going for C. So the place to start with this question is this relationship over here, that our total current, it's just the current from A plus the current from B. Now we know for any resistor, whether it's an individual resistor or a kind of hypothetical combined resistor, we know that the current is equal to the voltage divided by the resistance. So what we can do, we can take this expression over here and we can substitute it in to each of these three over here. So we have three pieces of the puzzle. And then the last thing we need to know is that in parallel, the voltage is the same. So those three voltages, they all just divide out. And what we're left with, which one is it over here? Over here, this one. So option C is the correct answer. So very well done, everybody who got option C, and especially if you gave the question a go, okay? Because the important thing with this is to give the question a go, try and figure it out. It's not such a big deal if you get a couple of things back to front. The main thing is to think about it, okay? But another very important equation whenever we're thinking about resistors, okay? So we can combine them in series or we can combine them in parallel. So let's try a numerical example with this one, okay? So, previously we had our 11 ohm resistor and our 7 ohm resistor, and if you just combine them in series, that's just going to be an 18 ohm resistor. Gets a bit more interesting if we think about combining them in parallel. So let's see what we get for these two resistors when we combine them in parallel. What's going to be the total resistance? All right, let's see what everybody gets for this one, okay? All right, so nobody's going for B and C. Some people going for option A, some people going for option D there. So the interesting thing with this question is that when we combine the resistors in parallel like this, we get a lower resistance than any of the resistors individually, which is kind of interesting. So they just behave as one big resistor, but with a lower resistance than 7 ohms or 11 ohms. And then when we say, okay, let's connect that to a 9-volt battery, what do we get there? We get the 2.1 amps of current. So looks like most people got that one. So very well done, everybody, with that question. Okay, because it can be quite counterintuitive to think, well, I've combined two resistors and I have a lower resistance than having them individually. One way I kind of like to think about it is if you think about a resistor as like a kind of a bumpy road or something, where you've got a lot of congestion, got a lot of traffic, your cars can't drive very fast on the road. If you have two of the roads, they're still going to be able to take more traffic than if you just have one, or if you have a 2-lane highway, your traffic's going to be able to move through there more easily, okay? And that's really what we've got when we have the resistors in parallel. Even though they're designed to impede the flow of current, make it more difficult for those electrons to travel through the material, when you combine them in parallel, you're essentially kind of making that roadway sort of wider for the electrons. So we get a lower resistance, okay? So that's what gives us this different current when we connect it to the same battery, okay? So very well done, everybody, with that question, okay? Now we're going to have a lot more practice with resistors in the workshop, okay? So make sure you give those questions a go, because they can be a bit tricky when we start this, but you get the hang of it once you've done a few questions, okay? Now, one of the times that resistors really come into their own and become really important is when we start combining them with capacitors. Now, who's studied capacitors before? Okay, very good. So, does anybody know what would we want to be using a capacitor for in a circuit? Any thoughts about that? Any thoughts? What we want to use a capacitor for in a circuit? Sorry, what was there? Store charge, absolutely right, okay. So we generally use capacitors to store charge in a circuit. So kind of a bit like a battery, but in a slightly different way. So let's take a look in a bit more detail about, what a capacitor is, how we use it, and how it works, okay. So I've got a basic diagram of a capacitor. And fundamentally, from a physics point of view, there's something that we use to store charge. And at the simplest level, they're just two parallel metal plates. Now, you might fairly say, well, hang on a minute. This diagram over here of a capacitor, it really looks nothing like this picture over, well, no, it's not a picture, it's a real capacitor. This capacitor over here, so what's going on? We'll get to that in just a moment, okay? But fundamentally, a capacitor, it's just two metal plates, two parallel metal plates, and you can put them in your circuit. And what happens with these metal plates, if we have some electrons coming from over here in our circuit, so we've got the electrons coming over here, they get to this metal plate and they can't go any further because there's just a big old gap. But what they do, they're gonna push the electrons over from that side of the plate. So what we get is we get charge building up on this side of the plate. So then even if we disconnect the capacitor from our circuit, we're still going to get a flow of charge. And this really brings us on to the kind of two things that we use capacitors for whenever we are building a circuit, okay? So we can use them to smooth out varying currents. So very often, especially in physics, if you're building a sensitive physics experiment, you don't want your current to be varying. You want a nice steady current. So quite often, the current that we get from the mains, it's not going to be super precise. If you're making something running on some nice direct current, you want a smooth current, a capacitor can help you out there. The other thing the capacitor can do for us is it can deliver current in bursts. So if we have a big old charge building up over here, and then we add in an extra bit of the circuit, let the current go around, that's going to give us a big old burst of current. Can anybody think of some examples where we use a capacitor to give us a burst of current like that? Any thoughts? Yeah. Sorry, where? A pulse laser. Yeah, absolutely right. When you want a big old pulse from a laser, yeah, great example. Any other examples where you'd use a capacitor, get a burst of current? Any thoughts?
You could use it as like a backup.
Use a backup, yeah, absolutely. If you want to smooth out your current, okay. So another good example. Do you guys remember, like not even before phone cameras, before even digital cameras? Do you guys even know what I'm talking about here? Like when they had the really, yeah, you're doing that, okay. And you had to look through the thing. Do you guys remember? And they had the flash. Has anybody even used one of those? Yeah. Use the what now? Exactly, 35mm with a film camera. Okay, so those old-timey cameras, when you had the flash, and it's not just like an LED, the light that turns on, that's powered by a capacitor. So I don't know, do you guys know what it's like? So you take the one picture and you get the flash of light, and then you have to wait for the capacitor to charge, and then you can take another picture. Okay, but then by then, everybody's gone home or whatever. So whenever you were waiting for the flash in your film camera to recharge, that's just because the capacitor was charging. So it charges up and then it gives you all that current in one go. You get that flash, okay? Any other examples of where you would want to use a capacitor, get a big burst of current? Any thoughts about that? So another very important example is in a defibrillator, okay? So if you're defibrillating someone, you give a big blast of current, okay? So do you guys, if you got, you watch the Casualty and the, all those kind of shows, you get the defibrillator charged up with current, that's the capacitor building up, and then you can jolt all that charge into someone, okay? So from a physics point of view, it's the same principle as, the flash on an old-timey camera. You're just charging up a capacitor and then delivering all the charge, okay? Now let's go back to this capacitor over here, because you might say, well, look, that looks kind of nothing like, this. I mean, this looks kind of like a battery. This just two pieces of metal. So what's going on? Okay. So quite often capacitors in kind of practical things, like you're going to get in a camera or in a defibrillator, they're not just two plates, because that's actually not going to store too much charge. So there's some things you can do to help them store more charge. Okay. So quite often, if you want to fill this with an insulator, stop the plates from touching, okay? And then also, you want to make these plates as big as possible, because that's going to allow you to store more charge, and then you're going to wrap them up, okay? So if you did, don't, but if you did dismantle one of these capacitors, okay, you're going to find it's filled with all this kind of gunk here between the two plates to keep them apart. That's the technical term for it, okay? And then it's all wrapped up in a big old spiral in here to kind of fit it in a can. So by doing that, you can fit a much larger area and you can store a lot more charge. You're not then having to go around with kind of big old metal plates everywhere. So that's the kind of basic idea with what's going on with a capacitor. Let's think about what's going on with the physics of a capacitor, how we really define it from a physics point of view. So in a capacitor, the charge, it's directly proportional to the voltage. So if we double the voltage that we're putting onto our capacitor, we're going to double the amount of charge that the capacitor is going to store. So similar kind of idea to the very first question we started with for resistors. Which one of these equations describes that relationship for a capacitor? So again, with this one, you don't need to guess. We know that the charge is directly proportional to the voltage. There's only one equation there which describes that relationship. So if you have seen this equation before and you can remember it, that's great. If you haven't, don't worry, you can figure out everything you need for it, okay? Okay, very good. Let's see what everybody thinks for this one here, okay? All right, okay, fantastic, 100%. Okay, this is what I like to see. So very well done, everybody, with this question. Okay, so correct answer is option B there. Okay, so our charge is directly proportional to the voltage. And the constant of proportionality, we use this capital letter C here. Okay, that's what defines how big our capacitor is. Okay, so very well done, everybody, with that question. Okay, now let's think about the units that we use to describe the capacitor there, okay? So the unit that we use, it's called a farad, okay? So the unit for that capacitance, it's a farad, okay? But let's think, how are we relating 1 farad of capacitance to the volts and the coulombs, okay, that we use to define the capacitance, okay? So have a think about this one. Let's see what everybody thinks for how to relate the units for capacitance. Okay, what are those units of farads there? So if you're not sure with this one, you don't need to guess. We know that our charge is equal to the voltage times the capacitance. We know the voltage measured in volts. We know the charge measured in coulombs. So we just need to think, what do we need for our units of capacitance to be to divide out the voltage and give us coulombs? All right, very good. Good to see those results coming in there. Let's see what everybody thinks. So, same kind of idea as this question with resistors. Okay, no one going for D. So, we know that our charge has to be measured in coulombs, and our voltage, it's measured in volts. So, whatever the units of this C are, they've got to divide out those volts, and they've got to multiply in some coulombs. So, that's option B over here. Okay, so very well done, everybody, with this question, especially if you got that it's option B. Okay. Now, before we move on and learn about a bit more about capacitors, there's kind of important bit of a confusion warning here. So I'd just like to have one slide as a bit of a confusion warning, because things can get a bit confusing, can get a bit mixed up when we're thinking about charge and capacitance and the units. Okay, so I'd just like one slide to kind of clear things up a bit, okay? And the reason it gets confusing is really because we start running out of letters of the alphabet. So if we think about these couple of variables, so charge, the symbol that we use to represent charge is a capital Q, okay? Now the unit that we use for charge is a coulomb, and the symbol that we use for coulombs is a C, okay? Now that's kind of fair enough. It starts getting confusing when we introduce capacitance, because if we're thinking about capacitance, so how big our capacitor is, the letter of the alphabet that we use for capacitance is a C, okay? So the symbol that we use to represent capacitance is also a C. So we've got this C over here for capacitance, and then we've got this C over here for coulombs. So I think you guys can see quite easy to get them confused, okay? And then the units for capacitance are farads, symbol is an F, okay? That's kind of fair enough, okay? So the main thing you've got to watch out for is confusing coulombs with capacitance, okay? Now the thing to kind of help you out is the convention that we try and adopt is that if we're having symbols to represent variables, we put them in italics, okay? So if you look here, the Q and the C, they're italicized, whereas symbols for units, they're not italicized. So this C over here, not italicized. Okay? So if you're reviewing, in the textbook or on the slides, that should help you out a little bit. Obviously, in your notes and handwriting, most people don't have, they're not writing kind of perfect cursive writing. So you would just kind of have to tell from the context, okay? But I think it's one of those things that if you're kind of aware of it, to kind of look out for. And you can usually tell from the context whether it's like, 1 coulomb of charge or, a capacitance of, 1 farad, something like that, okay? You can usually tell from the context, but do just watch out for that, okay? So I think let's try one question when we're kind of trying this as a numerical example, okay? Because turns out 1 farad of capacitance, that's actually a really big capacitor, okay? We generally use kind of smaller units here. So suppose we've got a smaller capacitor, so 4,700 microfarads, and then we connect that to the 9-volt battery that we've been using all lecture, okay? So let's think, how much charge are we going to be able to store on our capacitor when it's connected to a 9-volt battery. So if you're not sure about this one, you don't need to guess. We know that the capacitance is equal to the charge divided by the voltage. We know the voltage and we know the capacitance. So we just need to rearrange that equation, solve for Q, and see what we get. All right, very good. Good to see those responses coming in. Let's see what everybody thinks for this one. Okay, nobody going for A. Some people going for C. Most people going for B. So that 4,700 microfarads, so that's actually the capacitance of this particular capacitor over here. So that's kind of quite a typical capacitance that you might see if you're dealing with capacitors out in the wild there. Okay, and it looks like, as most people got, when you rearrange this equation, solve for Q, we get that it's the 42 millicoulombs over there. Okay, so if you connected this particular capacitor up to a 9-volt battery and let it charge up, we know exactly how much charge is going to be stored in the capacitor. Okay, so very well done, everybody, with that question. Okay, so that's a bit of a kind of introduction to capacitors. Okay, next time we're going to think about the physics of combining capacitors in circuits. Okay, and we're also thinking about the physics of how capacitors discharge. Okay, so that's the plan for next time. Okay, very well done today, everybody, with all the questions. Okay, and just a reminder, we've got the workshops tomorrow afternoon as usual then. Okay, so excellent work today. Hope you guys have a great afternoon, and I'll see you guys all tomorrow.